This video is about electromagnetic induction. You can go to this page on CK12 that I found. It's a nice page. It's explain electromagnetic induction, how it works. The page is ck12.org. Physics, well, you can try to find this page. I think it will not work directly on this video. So let's go to speak about electromagnetic induction, how it works, and let's go to the next. Well, imagine this is the basic idea of Faraday law. Imagine that you have a loop of a coil. Yes, you put a small you put like a copper here, a cable of copper here. Let me just a moment. So you put here a cable of copper. You have the magnet here. The magnet produces a magnetic field B. I put the magnet and the loop and the coil with no relative movement within them. What do I observe? Well, I observe nothing. So the first conclusion, I want to induce a current here. I want to induce a current here. This is what is about Faraday law. To induce a current on the circuit, on the loop, on the coil, by the magnetic field. So the first thing that I observe is that if there is no movement between the coil and the magnet, nothing happens. I cannot induce any current, or I cannot induce any voltage on the loop, on the coil, and then nothing happens. But if now I try to make movement, for example, I use this magnet, and I try to move the magnet in this direction, let's say going in this direction with some velocity, not maybe constant velocity also, maybe accelerate, it doesn't matter. What I observe a current on the loop, and a current means that is like a battery in the loop that has been created. It's a fantastic thing to create a current in the coil. So if there is a relative movement, then a current is induced on the coil and exists B sub E, electromotive force, in a way that this is the Faraday law. The electromotive force is exactly equal to the variation of the magnetic flux B respect to time. So let's go to study this equation carefully. This is what it says, the Faraday law. It says all what is writing here is what we are going to study in the next page. So the second thing that we can observe, 3 maybe, will be what happens if I leave at rest the magnet, and if I leave the magnet at rest, I might take the loop, I might move it in this direction. Will I observe a current on the loop, on the coil? Yes, I will observe electromotive force that will produce a current I, R by I, if the material is ohmic, of course. So is the relative motion between the field B produced by the magnet and the object that we are taking in consideration in this case is the coil, and what we observe is the flux. What will happen? So third things, if I move, third observation, if I move, so third observation is if I move the coil and I leave the magnet at rest, I will also observe a current on the loop. And the fourth observation is what will happen if there is a rotation of the loop? What will happen if I rotate the loop in a way that the flux is completely changing? For example, in this moment, the flux that cross the surface, this surface, will be zero. As he is rotating, he's facing the surface, so it's entering more flux. When he rotates 90 degrees, the flux will be maximum, and after that, the flux will be decreased and decreased. Okay, now we are going to study in detail this rotation of the coil that is in the presence of a magnetic field. The coil is rotating. So suppose that this is the magnetic field going up, this is the coil. The vector U sub n in this situation is going up. So we are going to rotate over the I-axis. The I-axis is this one. So let's say this is the x-axis. This is the y-axis. So U sub n is on the k-axis, on the zeta axis. So B is pointing out in the k direction in this case. Okay, so suppose we have this situation. This situation say that the loop is on at the presence of B. B is not changing. What is changing is that the rotation make the flux of this coil to change continuously. So in this, let's say that this is at t equals 0, phi is the maximum value that can have, and that will be the magnitude of B by the area. This is the flux, and the flux is maximum, and in this situation we say that theta is equal 0, because theta is the angle between B and U sub n. So in this situation, the loop have rotate 90 degrees, so the angle have rotate 90 degrees, and in this case, let me see, 90 degree, I have here, yes, 90 degree, and now the flux is 0. The flux is 0 because there is no crossing the surface. The surface is not being crossing through the surfaces. It's just tangent to the surface, so there is no flux. So the angle between B and U sub n is pi over 2. Pi over 2 is the angle between U sub n. So the angle is pointing out in this picture, is pointing out in the x direction. U sub n is going to your eyes, but in the x direction. So in this case, the flux is 0, and now the flux become negative in this situation because phi is pi, 180 degrees, and the flux become the minimum value, it become the absolute value is the maximum, but B become the minimum of all the values. So how it will do this graph of phi versus theta? Let's go to see. So if B is constant, let's go to find how it will be the graph and how it will be B sub B. So if B is constant, the flux is always B by the area by cosine of theta. But theta is changed with time, so I have to put theta of t. So the variation of the flux respect to time, this variation, the variation of the flux respect to time, will be B by A, that is constant, is going out of the derivative by the derivative of cosine of theta of t. Theta is changing with the time t, because it's rotating at some speed, at some angular speed. So the flux will be b by a by the derivative of respect to t of cosine of theta, and the derivative of cosine of theta of t respect to t is sine of theta of t multiplied by the derivative of theta by t. The derivative of theta by t is what we call the angular velocity, how much angle is rotating in how long. It is the ratio between the angle rotated and the time that have elapsed. So will be b by a, this is omega, omega by sine of theta, sine of theta. So this is b sub e induced. B sub e induced is minus b sub b by a by omega by sine of omega t. So if you want to graph this b sub e as a function of t, you will have to graph basically sine of omega t. So will be like this. The graph of b sub e as a function of the time t will be in t equals 0, sine of 0 is 0, and we are here at t equals 0. When t elapse some time t, sine of omega t become positive, but with this sign become negative, and when the angle omega t become pi over 2, when the time t become pi over 2 omega, sine of t will be sine of pi over 2. Sine of omega t will be sine of omega p over 2 omega. So will become sine of pi over 2, which is 1. With this minus sign will be minus 1, so this value is minus ba omega. So it will do like this. And this is b sub p, this is pi over omega, this is pi over 2 pi over 3 omega, 3 pi over 2 omega, and this is 4 pi over 2 omega, which is 2 pi over omega. So this is the graph. This is the maximum value when theta is 3 pi over 2, and this is the minimum value. So what I said from this side, that t is negative, the function will do like this. So what I said in the previous video, I think that when pi, let me see this. So what I said before was not about b sub p, was about this function, about the flux. The flux as a function of theta makes like b by a by cosine of theta. Cosine of theta is like this. Okay, cosine of theta, when theta is 0, is maximum, when theta is pi over 2 is 0, etc. So the flux is going like this with the angle theta. But what we are now graphing here is not the flux, is the chain of the flux, and the chain of the flux goes like this. This is the graph of the chain of the flux. So b sub e is negative when t is pi over 2 over omega. When t is pi over omega, let's say that omega is 3 hertz, 3 revolution per second, 3 revolution per second. So you will have pi over 6 here. So at this time, pi over 6 time will be like 1/2 seconds. In this case, you will have the minimum value of the electromotive force. This is the electromotive force induced. So let's go to the next story for this is what we are graphing, the electromotive force, and this is the flux as a function of theta. Okay, And the difference between the flux as a function of theta and V sub E is that the V sub E is obtaining by the variation of the flux, by the derivative of the flux respect to t. So not respect to theta, it's respect to t. So it's confusing. Don't look too much at this picture. Look at this picture. That is the picture that say where the electromotive force is going. And of course the current will be I will be V sub E over R. So if R, let's say, is 2, well, the graph will be like this, of I will follow the current and will be exactly the same graph as V sub E. And this is the graph of I. If R is equal to, is the same graph as V sub E divided by 2. Okay, so these are of the circuit. So ideas, let's go to, here I wrote, on this page I wrote something that I want to put you in the context. I want to be able to see the whole movie. And the whole movie is like this. Suppose that I have an electrical field, an electrical and an electrostatic field. This situation is what we are looking. We saw that if you vary the magnetic field, of course you vary the flux. If you vary the flux, you create an electromotive force. So we want to think about this in terms of the electrical field. To vary the electrical field, can we be able to induce a magnetic field if we vary the electrical field? Well, in the last situation for Faraday law, when we vary the flux, we create an electrical field. The variation of the flux, of the magnetic flux, create an electrical field. So now we want to study if it's possible to vary the electrical field and to create a magnetic field. So we start with this. If we are in a static situation, so the electrical field that we are dealing with become for charge that are not in movement, like this one. We know that the circulation of E is 0. We know that if you take and you make the work per unit of charge from going in a curve C, any curve C in the presence of the electrical field, you know that the total work from going to A, going back, and going back to A, the total work per unit of charge is 0 because this electrical field is a conservative field. The work that you do in this part, you lose it in this part. And the work that you do in this part from B to C is 0, and from C to A is 0. So what you do positive work from A to B, you do negative work from C to D. From C to D. Okay, so this is the idea that we deal always with electrostatic field. So we want to ask you, can an electrostatic field produce a current in the circuit? And the answer is, can we produce a current? If I put a loop here, and I put an electrostatic field here, an electrical field that doesn't change with time, it's electrostatic. Can the electrical field, if I put a coil here, produce a current? And the answer is no, impossible. It's impossible, not only because the circulation is 0, it's also because the cable have a little bit of resistance. So the energy per unit of charge that you make from going to A is 0. So you cannot gain any energy in going from A to A. But in going to A from A, you found resistance that take out energy, so it's impossible at the end to make a continuous current in the circuit, in the loop, by an electrical field that is static. So the meaning of this equation is that the electrical field is conservative, and also the meaning is that you cannot create currents using electrical fields that are not dependent on time. So when we put a battery here in the circuit to create a current, what we do is that the V sub P, the electromotive force of the battery, is exactly the circulation of E scalar DDL, the electrical field that produces the battery, that is moving the charge around the loop, around the coil. From A to A, they are moving the loop because this battery is supplying energy per unit of charge all the time. So in this case, the circulation of E scalar DDL is not zero. Is the energy of the battery per unit of charge. What energy is providing the battery? So we return to our question. Can we induce? So it's clear that we cannot induce a current with an electrical field that is static. So the second question is can we induce a current on a coil if we make the electrical field to change on time? If we make an electrical field E that is not only dependent on R, if you use an electrical field E that depends of R and T and the time T, can we induce a current? And the answer is yes. Is yes, and this is a very visual example that I'm going to tell you. Suppose that I have a positive charge here. Suppose that this is creating an electrical field here. So the electrical field, if I don't move the charge, if the charge stays at rest, I cannot get a current on the loop. It's impossible to get a current on the loop, but let's say that I'm approaching the charge a little bit in a way that the electrical field E depends of R and now depends of T, because now when the charge is here, the electrical field here is more intense because it is near the circuit, so has changed at the same point. Let's see, the same point. At this point, the electrical field has a value when the charge was here, and now the electrical field when the charge is here have a bigger value. So we can put like this. This is the electrical field at this value, but when it's here, the electrical field is bigger. And at this point now, the electrical field is smaller. So I'm moving the charge. I can get that the movement of the charge, this positive charge that creates the field, make that at any point the electrical field is changing. So I can make a current here because in this situation, the circulation of E scalar DDL around the core will not be zero, because when I go from here to here, the circulation every time will be bigger, and when I go from here to here, the circulation will be smaller because the electrical field is smaller because the charge is now farther. So I can make an electrical field changing with time to be able to create a current on a loop. But the electrical field has to be not an electrostatic field like this one that doesn't depend on time. Have to be an electrostatic field that depends on time. Good. Let's go to the next page. This page is the same thing. If Faraday law say that whenever you have a change in the flux of the magnetic field, let's go to put it here. Whenever you have a change in the flux of the magnetic field, you have an electromotive force. And this electromotive force, this one is the electromotive force that you will induce, is the variation respect to time of the flux. But we have to interpret correctly this minus sign. This minus sign is saying that the electromotive force will oppose to the change in the flux. If the flux is increasing, the electromotive force induced will oppose in a way that will try to create a current in the opposite direction, in a way that you oppose not to the flux, you oppose to the variation of the flux. If the flux is growing up, it means that the variation is positive, so the electromotive force V sub E will be, if it's positive, the electromotive force will be negative with this minus sign. So the best way to see this is to see some examples and to study a few examples. Let's go to do it. And before doing this, I want to say that the electromotive force is always the circulation of E scalar DDL. This E is a non-conservative electrical force. As you know, V sub E, what it say Faraday law, is that V sub E is minus the derivative respect to time of the flux. The flux can be written like B by A by cosine of theta approximately. So this variation is the variation of three terms. Three terms can vary. If B change, the magnitude of B change, let's go to put here the magnitude of B. So the product rule for this variation is that the variation respect to T of this quantity B by A by theta means that can vary V, and A and theta cannot vary. This is the first term. Can vary A, the area can be bigger or lower. So if you make the area lower, you also induce electromotive force, and the variation will be minus B by B minus magnetic field by the derivative of A respect to T by cosine of theta. And also you can vary, or you can maintain B and A constants, and you can vary cosine of theta. So the variation of cosine of theta will be sine of theta, of course, by the derivative of theta respect to T. So there are three terms that can make possible to make variation and to obtain V sub E. Normally in problems you have only one of the term working. Maybe it's B that is changing, is growing up, and so the derivative of B respect to T is positive. Maybe it's the area that is going bigger or lower, or maybe it's the angle that is changing, like the rotating coil that I explained you how to induce electromotive force in a rotating coil. So any of these three terms can appear. Normally in problems only appear one of the terms. So you have to see what of the term is appearing and use the equation B sub E, depending on the term that is appearing, to put the correct term in. And B sub E, of course, is equal to the circulation of E scalar DDL. So the circulation of E scalar DDL is different than zero. So if it's different than zero, it's meaning that E, the electrical field, is not conservative. It's not conservative force, and of course, this will be equal to the resistance by the current. V sub E will be the resistance by the current. So let's go to analyze a few examples. This is our target is to solve some examples and to see the real meaning of this minus sign. Okay, let's go to the next page. Let's go to the next page, and this is the formulation of the Faraday law again. It's exactly just the same. The flux is this, and the electromotive force is this one, the variation of the flux, and the minus sign is this one. And what I did here is the flux is this quantity, B by A by cosine of theta. So it can be changed in respect to time if B change with time, or if A change of time, or theta change with time. So I want to resume the three changes using the product rule of the derivation of the derivative. So will be the derivative of the first by the others, plus the derivative of A respect to t by the others, plus the derivative of the others by the derivative of cosine of theta, which is sine of theta by omega, dd theta by the omega. So normally in problems you have three terms. You have one of these terms that is involved in the chain of the flux. The change in the flux is due maybe because the magnetic field is changing, maybe because the area is changing, or maybe because the angle is changing, or maybe because everything is changing, which is more complicated. If the conductor follow the Ohm's law, then V sub E is R by I. And let's go to the next page to see what happened. This is one example. We did this example in class. We have a loop. We have a magnetic field. The magnetic field is going through the screen, through my screen, and we wonder if if B is changing, how it's changing? The change of B by T is 0.2 Tesla by second. So if this magnetic field is changing, so the flux is changing. So here the magnetic field is changing because the flux is changing because the magnetic field, this magnetic field is changing every time there is more flux. So the flux is changing only because B is changing. It's not because the area is changing or the angle is changing. So the equation that you have to find is that the electromotive force induced is the derivative of the magnetic field respect to time by A cosine of theta. Cosine of theta is 1 because V and the area is parallel, so cosine of theta is 1. So in this case, V sub E is derivative of V respect to T is 0.2 by the area pi over R squared. So you have V sub E, and you can find the electrical field induced. And the electrical field induced, you have to suppose that there is a symmetry here that allow you to think that the electrical field will be like this. But will be like this or will be in an opposite direction? Well, the idea is this minus sign. This minus sign will tell you in which direction it is. This electrical field will produce a current in this direction. If the current goes in this direction, this current will produce a magnetic field going to my eyes. So if the magnetic field going to my eyes is going to be opposed to the increasing flux of magnetic field. So this is the correct direction of E and the correct direction of the current. The currents go like this, follow the electrical field, of course, and the direction should be like this because the minus sign, and this is the length law, say that the currents always create a magnetic field that oppose to the change in the flux of the magnetic field. We saw this on the other video, and we saw the same idea on class, and let's go to the next page. So if you want to find the electrical field, you use this equation, and I suppose that in this page I have used it. So V sub E is 0.5 pi over R. E is the symmetry of E is over the curve C it is supposed that E is tangent to the line. So if it's tangent to the line, this circulation is E by 2 pi r, and this allows us to find the electrical field, and this is the electrical field that I found it. What else? Here I explain the direction maybe. There is something else that I explain. Here I wrote again the Faraday law. And I want to tell you something about the surface. The Faraday law says, now I'm quiet, no so much noise. So there are two details here that I wrote. The first detail that I wrote here is the following one. You have the derivative respect to time of the integral, the derivative respect to time of the integral over the surface. First detail, this surface is an open surface, it's not a closed surface. But this circulation of the curve is over a curve, and you go across the curve. You go around the curve and you close. You go from point A, let's say this point A, to point A. It's a closed circulation of E. But this surface, as you see, is here an open surface. So the open surface, I don't put here this symbol. This symbol, I'm not putting this symbol here. I don't put it this symbol. So let's go to take it. I take it. I take it. I take it. I don't put because it's not a closed surface, it's an open surface. So the question is, when you use Faraday law, which surface are you meaning? Are you meaning this surface? Or are you meaning this surface, for example? You have seen, this is the curve. You have seen a kippa, for example. Well, the surface make like this. It's open here, but it makes like this. Or maybe this is the curve and it's a general surface. Imagine, for example, your plastic bag from garbage. You open it. This is the curve, the entrance for the bag, and this is the surface. No, this is the surface. So this surface S is which one? Is this one? Is maybe this one a little bit distortion, or is this one? Well, this surface is any surface with that is enclosing the surface, that belong to the curve C. So it's any surface. Can be, if the curve C is this one, it can be this one, it can be this one, or it can be an O, any surface C. Yes, any surface that is with the sustent of the curve C is a valid surface for Faraday law. And the second detail that I want to mention is if you want to put this inside the derivative, you have to, because B and maybe S depend on T, you have, of course, to use the partial derivative of the partial derivative respect to T. You cannot put the total derivative inside this integral because B depend on the position and depend on time. So this is the Faraday law. Writing correctly, where S is an open surface that is sustained by the curve C, and this is the partial derivative respect to time. So let's go to see next. So the next page, what I suggest you to do is the following problems that I'm going to mark. This problem I consider you should know, 29.7. You can try to do all these problems between today and Sunday. And Sunday I will be willing to help you to do this problem with a lot of pleasure. So I will be from 10 to 12 on Sunday on Zoom for anyone that want to discuss any of these problems. Any one of these problems, we can discuss, we can make the problems correctly. I can give you the idea how to do it, and I can help you whatever I can. So this problem 29.7, this problem 29.16, 18 and 19 I like, you should make it. 29.25 and 29.26 also I like, you should do it. It's important. And I think that you have to solve the following example from the textbook, similar at those who that we solve on class. Just a moment, and that you know how to do it. And this problem 2946, you should do it, and this problem 2935. So good luck, make the problems, only if you want. You should do. If you don't want to do it, don't do it. No, I'm joking. You must do it. You must do it because this will check if you are understanding. If you know how to solve this problem, it's because you have the idea how to do it. The concept is clear in your mind. So practice the concept applying to these problems that are not difficult. As always, I wish you good luck.